Welcome back, everyone. We're diving deep today into the fundamentals of electromagnetism, specifically electromagnetic induction. We're going to crack open a physics textbook, Chapter 6, and really see how electricity and magnetism are connected. It's pretty amazing how something discovered nearly 200 years ago still powers our world today.
Yeah,
Power grids, electric motors, all that stuff.
it really is remarkable.
So let's rewind a bit. For a long time, people saw electricity and magnetism as like totally separate things.
Yeah, completely different.
Like two ships passing in the night.
Right.
You had your folks playing with static electricity and others messing around with magnets, but nobody really put two and two together.
It was a real missed connection.
Then, in the early 1800s, guys like Oersted and Ampere came along and started noticing some intriguing stuff. They saw that when you have moving electric charges, you create a magnetic field.
Huge turning point. Huge. It was like the first real hint that these two forces were somehow, related.
Yeah, like those shifts weren't so far apart after all.
Precisely.
Then boom. Around 1830, Michael Faraday and Joseph Henry came along and kind of flipped the script entirely. They actually figured out that if you move a magnet around, you can create an electric current.
It was a game changer, for sure.
Like in one of their experiments, they took a bar magnet and moved it near a coil of wire.
Simple as that.
And suddenly, bam,
Right.
electric current in the coil.
And the faster they moved the magnet, the stronger the current got.
Interesting. So it's not just the magnet itself, it's the movement, the change that matters.
It's all about the relative motion between the magnet and the coil. That change in the magnetic field around the coil is what induces the current.
Makes sense. Now, our textbook talks about a few other experiments that Faraday and Henry did. Do they all kind of have the same sort of takeaway?
Definitely. Whether they moved a bar magnet near a coil or moved a coil carrying current near another coil, same result. Induced current. And what's even more interesting is that in one experiment, they didn't even physically move anything at all. They just changed the amount of current flowing through one coil, and boom, that change created a changing magnetic field, which in turn induced a current in a nearby coil.
So it seems like the big takeaway here is that it's a changing magnetic field near a conductor that creates the electric current. It's not just about the magnet, it's about that dynamism, that fluctuation.
Absolutely. And that's where we get to this concept of magnetic flux.
Okay, magnetic flux, what is that?
Oh, well, you can think of magnetic flux as the amount of magnetic field passing through a certain area. Imagine like holding a hoop in a magnetic field. The number of field lines passing through that hoop, that's your magnetic flux.
Okay, I can kind of picture that. So what determines how much flux you have?
Well, there are three main things. The strength of the magnetic field itself, obviously, the size of the area you're looking at, and then the angle between the magnetic field lines and that area.
So stronger magnetic field, more flux, bigger area, more flux. What about the angle?
Think of it like rain hitting a window.
Okay.
If the window is tilted right into the rain, you're going to get more water hitting it than if it's, slanted away. Same with magnetic flux. The more directly the magnetic field lines hit the surface, the greater the flux.
Ah, that makes sense.
Yeah.
So we've got these moving magnets, these changing magnetic fields, and this idea of magnetic flux. How does it all connect back to Faraday's big discovery of induced currents?
Well, that's where Faraday's law of induction comes in. This law basically says that the strength of the induced electromotive force, or, EMF, which drives the current, is directly proportional to the rate at which the magnetic flux is changing.
So the faster the magnetic flux changes, the stronger the induced current.
You got it. It's not just about the magnetic field. It's about the change in that field, the fluctuation in magnetic flux.
Yeah.
And that, my friend, is the foundation for how we generate electricity. Every time you flip on a light switch, thank Faraday's law.
Wow, that's pretty mind-blowing. But wait, there's another law here too, right? Something about energy conservation.
You're right. We can't forget about Lenz's law. This law tells us that the induced current always flows in a direction that opposes the change in magnetic flux.
So it's like the induced current is pushing back against whatever is creating it. Why would it do that?
Energy conservation. It's all about energy conservation. Imagine a loop of wire moving into a magnetic field. As it moves in, the flux through the loop increases, which induces a current, right? Now, if this current didn't oppose the change, you'd have this runaway effect where it creates a stronger magnetic field, which then induces an even stronger current, and so on and so on. You'd be creating energy out of thin air.
So Lenz's law is like the universe's way of keeping things balanced.
Exactly. You can't get something for nothing. It's why those perpetual motion machines you hear about are well, impossible.
That's fascinating. So we've been talking about changing magnetic fields from moving magnets. But can you induce an F by just moving a wire through a magnetic field?
Oh, absolutely. Our textbook has this great example of a rotating rod acting like a moving conductor in a magnetic field. As the rod rotates, it cuts through the magnetic field lines, and, well, that motion induces a voltage.
And that ties back to Faraday's law. Right. Even though it's just a single wire moving, it's still changing the area the flux is passing through.
Exactly. It all comes back to that change in flux. Now, before we get to how this all fits into a generator, there's one more concept we got to unpack. Think of it like the inertia of electrical circuits. It's called inductance.
Inertia for circuits. Okay, I'm all ears. Tell me more about this inductance.
So inductance is basically a measure of how much a coil resists changes in current. We denote it with the letter L. You can think of it like this. A coil with high inductance is like a heavy object. It takes a lot to get it moving, and once it's going, it's hard to stop.
So, like the electrical version of inertia.
Exactly, and it all comes back to those magnetic fields. When the current through a coil changes, well, that creates a changing magnetic field, and a changing magnetic field, like we've been talking about, can induce a current, in this case, a current in the coil itself.
A coil can induce a current in itself. That's crazy.
It's like a feedback loop, right? And the self-induced current, thanks to Lenz's law, it always opposes the original change in current. That's what we call self-inductance.
Okay, so that's self-inductance. But you mentioned another type too, right? Mutual inductance.
Right, right. Mutual inductance happens when a changing current in one coil induces a current in a nearby coil. Same principle. Changing current, changing magnetic field, induced current. But now it's happening between two separate coils.
So mutual inductance, that's how transformers work, right?
Yeah.
Stepping voltage up or down as needed.
Exactly. Transformers rely on mutual inductance to transfer energy between circuits without any direct electrical connection. But let's not get too sidetracked with transformers. We've got bigger fish to fry.
You're right. Time to talk AC generators. I'm ready to see how all of this comes together. Faraday's law, Lenz's law, inductance, all of it. How does it all work to power our world?
Okay, so the heart of an AC generator, it's actually pretty simple. You've got a coil of wire, and it's rotating inside a magnetic field.
And as the coil spins, its orientation to that field changes, meaning the magnetic flux through it is changing constantly.
You got it. And that changing flux, thanks to Faraday's law, it induces an electromotive force, or EMF. That's what drives the current. If you look at figure 6.13 in the book, you can see the basic setup.
Got it. So the faster the coil spins, the faster the flux changes, the stronger the current.
Exactly. But here's the thing. The induced current isn't just flowing in one direction. It's alternating. It changes direction every half turn of the coil.
Why is that? I thought a changing magnetic field just makes a current. Why would the direction switch back and forth?
Okay, picture the coil spinning in the magnetic field. As one side of the coil moves up through the field, the induced current flows one way, but when that side swings back down, the current reverses. It's this constant back and forth motion that creates what we call alternating current, or AC.
Oh, so like a wave, going up and down, positive and negative.
Perfect analogy. And the faster the coil spins, the faster the current alternates, which is why AC power systems have a frequency. That's just the number of times per second that the current changes direction. 60 hertz in the US, meaning it changes direction 60 times every second. A lot of other places, it's 50 hertz.
It's mind-blowing that the electricity we use every day basically comes down to spinning magnets and coils of wire.
Pretty neat, right? Now, you might be wondering, why does the coil have to spin? Couldn't you just move a magnet back and forth near a stationary coil to get the same effect?
Yeah, good point. Seems like it would work.
It would, but when you're talking about generating power on a large scale, rotating the coil is much more practical, much more efficient.
The textbook also mentions that in real-world generators, it's usually the magnets that rotate, not the coil. Is there a reason for that?
Great question. The coils in a power plant generator are huge. Spinning them would be incredibly difficult, not to mention inefficient. Much easier to spin the magnets, which are usually electromagnets, around the coil.
Yeah, that makes sense. And probably easier to manage the electricity coming out of a stationary coil, too. Speaking of, where does the energy to actually spin the magnets come from?
That's where things get really interesting. Most big generators get their spinning power from turbines.
Like those giant windmills you see in wind farms.
Those are wind turbines, yep. They're definitely a big source of power these days. But there are other types, too. Hydroelectric dams use the force of falling water to spin turbines. Thermal power plants use steam to drive turbines. They make that steam either by burning fossil fuels or from nuclear reactions.
So no matter where the energy comes from, you just convert it into rotational energy to spin a generator and make electricity.
Exactly. And it's not just massive power plants that use this. Remember the bike example from the
Oh
text?
yeah, I love that one. So even a bicycle can be a generator, right?
It can. You can use human power, wind, heck, even ocean waves to spin a generator. The scale might be different, but the science behind it is the same.
It's amazing to think that all of this electromagnetic induction, is at work everywhere, powering our homes, those little lights on bikes. We started with some simple experiments, and now we're generating electricity.
It really goes to show how powerful Faraday's and Henry's discoveries were. Hard to imagine our world without being able to generate electricity on demand. But as groundbreaking as their work was, it was really just the beginning of a much deeper exploration of the relationship between electricity and magnetism.
Now you've got me curious. What do you mean? Is there more to this story? So we've seen that moving magnets can make electricity, but where else can we go from there?
Well, remember way back at the beginning, we talked about how moving electric charges create magnetic fields. That was kind of our first clue that these two things were connected.
Yeah, it's pretty amazing how those early experiments opened up a whole new world of understanding.
It really is. And that leads us to this question that physicists thought about for a long time. If changing magnetic fields create electric fields, could the reverse be true? Could changing electric fields create magnetic fields?
Whoa. So, could the dance partners switch roles? That's a pretty cool thought.
It is. It's all about symmetry in nature, right?
Huh.
And the answer, it turns out, is yes.
So it's not just that moving magnets make electricity, but changing electric fields can actually make magnetism. That seems like a pretty big deal.
It is. It means that electricity and magnetism aren't just related, they're two sides of the same coin. Really, they're both just different aspects of this single, unified electromagnetic force.
Okay, my mind is officially blown. Did Faraday and Henry figure that out too?
They laid the groundwork, but it was James Clerk Maxwell who really put it all together in the 1860s. He developed these equations that describe exactly how electric and magnetic fields interact and influence each other. And get this, his work actually predicted the existence of electromagnetic waves.
Wait, electromagnetic waves, you're talking about light, right?
Bingo! Light is an electromagnetic wave. And Maxwell's equations, they showed how it's created, all from this interplay of changing electric and magnetic fields.
Wow. So we go from those early experiments with magnets and coils,
Mhm.
and we end up understanding light itself. That's incredible.
It really highlights the power of scientific curiosity. And it all started with this simple question: could changing electric fields create magnetic fields?
This is why I love these deep dives. You never know where they'll lead. We started with the basics of electromagnetic induction and ended up talking about the unification of electricity and magnetism and the nature of light, giving me a whole new perspective on how everything works.
And hopefully it sparked some more questions for you, too. That's the beauty of science. There's always more to learn, always another layer to peel back.
Absolutely. This deep dive has definitely left me with tons of new questions to explore. I think I'll be spending some time digging into Faraday's experiments and Maxwell's equations.
That's the spirit. Keep that curiosity alive. Never stop asking questions.
Thanks for joining us for this electrifying journey into electromagnetism. We'll see you next time for another deep dive.